Hi, this is JF with you today to discuss the hypergeometric distribution. A variable that obeys a hypergeometric law is characterized by the following features. There are n elements that are to be selected without replacement from a population of size capital N. The population itself consists of ns elements that we consider successes. All other elements are failures. Variable x counts the total number of successes that were observed over the n selections. When it comes to labeling a hypergeometric law, we shall write that x obeys a hypergeometric, little n is the number of selections taking place, capital N the population size, and capital NS is the number of successes within the population. For example, suppose a group is formed of 26 students, from which 19 are girls and 7 are boys, and you must randomly form a committee of 5 students. If X represents the number of boys that were selected onto the committee, then X obeys a hypergeometric. 5 is the number of selections taking place, 26 is the population size from which selections are made, and 7 is the number of successes within the population. Suppose that you select 10 marbles without replacement from a container that has 70 white and 30 black marbles, and let Y represent the total number of white marbles that you selected. This time Y also obeys a hypergeometric, which consists of n selections, 10 in this case. 100 is the population size, and 70 is the number of elements that are considered successes within the population. Finding the expected value, the variance, and the standard deviation for a hypergeometric variable requires certain formulas. The expected value will be the product of the number of trials or number of selections times the ratio of ns over n. If you think of that ratio as being p, you will recognize a binomial law, or at least the same formula as we use for a binomial law. However, when it comes to variance, the formula is very different than that of a binomial, and let's spare ourselves the proof for this formula. Standard deviation is the root of the variance as usual. Now, if it comes time to calculate the probability for a specific value of x, we also have a formula. So we are counting at the numerator the different number of ways to actually obtain k successes. The first term, in the first term, we are choosing from the ns successes in the population, k of them as being successes. The remaining selections, n minus k, must be selected from the failures. So the numerator is actually just a counting method. The denominator is the total number of ways of selecting n elements from the population. You can calculate probabilities on your calculator. There are some tables that can be found, but more often than not, we'll simply use Excel, which is conceived to do this kind of calculation. You will find the hypergeometric law in your Excel sheet under the name Hypergeomdist. For example, 50 students who are riding the 124 bus to Marinopolis. Let's assume 18 of those students are writing a test on that day, which means 32 are not. You select 10 students at random from this group without replacement to complete a questionnaire. If we denote by X the number of students riding the 124 bus who will be writing a test that day, then X is definitely a random variable. Within the 10 that you select, perhaps none of them will be writing tests, and perhaps all 10 will be writing a test that day. Does X obey a hypergeometric distribution? Well, Yes, because of the properties that go along with it. There are 10 elements that are selected without replacement from a population of size 50. The bus is divided into elements that are successes, there are 18, and that are considered failures, there are 32. And variable x counts the number of successes over the 10 selected individuals. How would we label x in this probability case? Well, we'll say that x obeys a hypergeometric, where 10 selections take place, 50 elements form the population, 18 of which are successes. How many students do you expect to select in the 10 that are writing tests? Well, here we go. So we've got our different formulas for the expected value, the variance, and the standard deviation. So in your sample of size 10, you would expect 3.6 of them to be writing a test that day. And that number could very well fluctuate by 1.37. What is the probability that exactly 4 students in your sample will be writing a test? Well, you can use your counting techniques and say that from the 18 that are writing tests, 4 have to be chosen, 6 from the 32 not writing tests, and your denominator are the total number of ways of selecting 10 elements from 50. Or, once again, you could use Excel. What is the probability that 3 or more students in the sample will write a test that day? Here we have to be a little bit careful, because having 3 or more is the opposite of having 2 or less. If we're going to use the formula we saw in the previous slide, we would probably prefer to use it on 0, 1, or 2 elements rather than on 3, 4, 5, 6, and all the way to 10 elements. Also, Excel has a feature that allows you to add up the cumulative probabilities for a number and those that precede. So you'll notice in the bottom window of our Excel function, I have placed a 1 to say that I want to add up all probabilities for 2 or fewer successes.